All right, this is 14.8, second example. This is another classic example. So by classic, I mean in the first two and in this one, if you got something similar, then you would do a similar sort of substitution. And not all problems are quite like this, but these three are nice because they're common and they have sort of fairly easy to see substitutions and they work out fairly nicely. So for this one, let's say find the integral over r of xy dA, where r is the region x squared over 4 plus y squared over 9 equals 1. Or sorry, less than or equal to 1. So if it's not clear what this is, you might notice that if you had an equal sign here, right, if we had x squared over 4 plus y squared over 9 equals 1, it's an ellipse. And the way to see the intercepts of this is simply to plug in y equals 0 and x equals 0. So when y equals 0, we have x squared over 4 equals 1, so x is plus or minus 2. And when x is 0, y is plus or minus 3. So what our r is also an ellipse, it's just filled in. So if we drew a picture of it, it would look like this. 3 in the y direction, 2 in the x direction. This is not exactly drawn to scale, that's okay. Like that. And so the way to see what to do here, in the first example, we had a parallelogram, we turned it into a rectangle. The second example, we had something that still had 4 sides and we turned it into a rectangle. This one, it's an ellipse, which is close to a circle. So what we'll see is like, well, can we make a substitution that turns this into a circle? So can we make a substitution which changes r to a circle? So take a look at the equation, or even the inequality. So I'm going to rewrite this as x over 2 squared plus y over 3 squared less than or equal to 1. What that allows us to see is if we made u equal to x over 2, and if we made v equal to y over 3, so let's say let those be the case, then we get, let's say this becomes u squared plus v squared is less than or equal to 1, and that's a circle. Again, in the UV plane. So that would look like this. You redraw this in red. Circle of radius 1. That is our S. This back here on the lower left was our R. So S is much nicer than R because it's circular. So again, all we need to know is we need to know the Jacobian, and we need to know what the integrand is. Now notice the integrand, the xy here, it's not obvious what it is. We need to know what x and y are for this. So here, if you look back at the substitution, remember the substitution was right up above it, right there. These two guys right there. So if you take a look at those tell us that x is 2u and y is 3v. So xy is 2u, 3v, which is 6uv. That's the integrand. Now, interestingly, because we've solved for x and y, we can use the other form of the Jacobian, right? So because we know x equals and y equals, we can do the Jacobian. Remember, the first version, one of the two versions we gave, was the determinant of partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. Partial x, partial u is 2. Partial x, partial v is 0. Partial y, partial u is 0. Partial y, partial v is 3. So those calculations, just so that we're clear, those are coming from being circled right here. That's what we're using in that calculation to get that Jacobian. So this is just 6. Very nice and easy. So then we have the integral over r, the beginning integral becomes integral over s of the integrand is now 6uv. The Jacobian is 6. That's the absolute value of 6. The absolute value doesn't matter, but putting there as a formality because the formula had it. And then dA, right? So now stop and take a look at this, right? S is a circle, which we would traditionally do in polar. So I'm going to redo it in polar, but since the current axes are u and v, we're sort of doing a slightly different polar change. So we're going to use polar, but traditionally x is r cosine theta, but the x here is the u, so u is r cosine theta. The v is r sine theta. So what we get here is we get theta goes from 0 to 2 pi. Radius goes from 0 to 1. We have a 36 here, so we'll put 36. The u becomes r cosine theta, r sine theta. Then we have a Jacobian r d theta. Now, and then we just evaluate. But before I close up, let me just sort of make a comment here. When we do this polar, this is yet another change of variables. We don't think of it that way because we're just doing a polar parameterization. But this is the Jacobian, which arising from this additional change of variables right here. So that original r that came up back in the section on polar coordinates, this is where it came from. It came from doing that assignment. So at the end of it, though, we just evaluate and call it a day. So that's the end of that problem. So next I'll do a fourth one or a third one, depending how you're counting, which is not at all as clear as either of these in terms of the substitution that might be made.